All right, how's it going today? We're going to be learning to use this measurement tool, the Vernier Video Analysis app, to analyze some motion. Specifically, we're going to be using it to make a position versus time graph of motion. You should also use it to make velocity versus time graphs of motion, but for the sake of time, we'll just do position versus time today. We're also going to see how we can use this. Well, we can use this to make a measurement of any unknown kinematic quantity, but today we're going to use it to make a measurement of the acceleration of our little friend, the ErgoBot here. So I've loaded up the video. I can use this to kind of scrub back and forth through the video. You know, if I can play the video, I can see our friend ErgoBot here accelerates to the right, starts out slow and speeds up. Well, I'm going to set it up to right after he just starts moving. Right, you got to think about what you're going to analyze. I'm going to analyze the whole motion, but I want to wait till he actually starts moving. So right about here is fine. Let's see. All right. So the first thing I want to do is make a prediction about what I'm going to see. I just watched that motion. I saw him accelerate to the right. You got to make your prediction before you do your analysis, otherwise it's cheating. And if you don't have a prediction, then it's not even science. So let's see. I noticed that he sped up, started out slow and sped up to the right. So I know that the graph, the position versus time graph, will generally go upwards. Since he's moving to the right, it'll start out flat and get steeper, because I know a flat position versus time graph is a small velocity and a slow speed, and a steep position versus time graph means a large velocity and a large speed. Okay, and it's all going to be positive. Okay, that's my qualitative prediction. My quantitative prediction, I want to give a number for my acceleration. I predict the ErgoBot will accelerate at, well, there's a lot of ways you can make a prediction. You can make a wild guess. But I happen to know, or well, I don't know, but I programmed it to go at 0.03 meters per second squared. I predict that it's going to go that because that's what I programmed it to do. Okay, there's besides making a wild guess or programming something to do something, you can also make your predictions based on an educated guess, based on an independent measurement, based on looking something up, based on setting up an experiment. Maybe you do a careful calculation. Right? There's a lot of ways to make a prediction. As long as you make a prediction and it has a number and it has a unit, it's fine to be wrong. But if you wait till after, it's fine to be wrong because you learn from it. But if you wait till afterwards, it's cheating. So let's see. We've got our prediction. So now let's take our data. Well, I'm also going to go up here. I'm going to turn off Y because we're just looking at X today. And the first thing we got to do, or I guess the next thing we got to do, is make sure that we set our coordinate system. So the way that this app knows how far one pixel represents is by setting the scale. That's why you need to have a meter stick, or it doesn't have to be a meter stick, but anything that you know the length of, you set it up here. It defaults to a meter, but you can change it. So now that I've set this, it knows 1,238 pixels in my video is 1 meter. I'm also going to set the origin of the coordinate system, right? Where does x equal 0? I'm going to make x equal 0 right at the beginning of my meter stick. And I noticed my camera was a little angled, so I can rotate so that my x-axis goes along. So my x-axis is along the flat table. All right. So now that I've set my coordinate system, I'm ready to take data. So the part of the object that I'm tracking is the blue light on my ErgoBot, right? You always need a kind of a clear part of the object that you're tracking. That's one thing that makes it a trackable object. So the blue light should be good. I'm going to put the target right over it, and I'm going to adjust the circle so the blue light's inside of it, but not much else is. All right, and now I can start. Actually, I'm going to put on my data table and turn off the notes. And now that I've set my target, I can just start auto tracking. Oh, it lost it. So if it loses it, that's okay. You just put the target right back over the blue dot. I might need to make it a little bit bigger. Maybe I made that target too small. Make it a little bit bigger. And I'll start again. And there we go. So now it's making the graph. It's going to take a lot of data points. The more data points, the better your measurement. And this is a great tool because you can make a super accurate measurement with just your Chromebook or whatever device and a video camera. And in physics, we love to make super accurate or super precise measurements. Hopefully they're accurate as well. Okay, so we lost it again, but we just put the target right back over, start auto tracking again, and you can look, our graph gets made. We've got 132 data points so far and counting. It's still going. We've got a column for our time, how much time since our first data point. The position is how far we are along the x-axis from our origin in meters. I lost it again, but we put it right over and start again. And if it misses a few frames, it's time. If it misses a few frames, it's fine. You've got so many data points. A couple of weird ones will average out. And there we go. We can probably stop there. Okay, stop. Okay, so there we go. Look, we have, now let's put the graph front and center. We've taken our data. Now we can analyze it and see if our predictions were good. So let's turn off the data table with our numbers again. Oh, one other thing, if you get really weird data, it's better than trying to fix a couple data points. You can always just start over. The three dots next to data set, you can delete it and start over because it's pretty quick and easy to do. I'm going to turn off the data table. So my graph is kind of front and center. But look, my prediction seems pretty good. It goes upwards, it starts out flat and gets steeper, right? Now we want to see if was my quantitative prediction right. What I'm going to do is fit a quadratic to this, right? Because in our constant acceleration model, our big 4 equation number 3 is a quadratic equation. I'm going to highlight my data, but not that kind of end stuff after it stopped. So just kind of, highlight most of it, but usually sometimes at the beginning or at the end there's weird stuff, and if you can feel free not to highlight that. We've got so many data points, it doesn't matter. Let's do applied curve fit, and we don't want to fit a line to this data. It's a quadratic, and apply. Okay, so let's kind of move this over here. So now we've got a whole bunch of numbers. What does that mean? Well, we know that our big 4 kinematic equation number 3, our position versus time equation for a constantly accelerated object, is position is our initial position plus plus our velocity, initial velocity times time plus 1/2 our acceleration times time squared. That actually matches up with this quadratic formula here. If you kind of have to translate and remember that in the quadratic formula, x squared, our time is the x-axis, so time is really x here, and our y-axis has our position, or x, so that can be confusing. But what that really means is that the term that has the quadratic term, the time squared term, is really this one, and a here corresponds to 1/2 of our acceleration, and that is best discussed in detail elsewhere. But what that means is our acceleration, and let's turn on our uncertainty. What that means is oh wow, that's pretty good. What that means is our acceleration, perfect. If we go to notes to continue our prediction. So let's see how we did. Our graph looked just as predicted. Our acceleration is 2 times, we have to double the a parameter from our quadratic. So it's 2 times 0.015, which happens to be 0.03. And it does, wow. And our uncertainty here, this is how many decimal points we are good to. So our uncertainty here is very small, right? This is plus or minus. So our acceleration, or half of our acceleration, is 0.015 plus or minus 0.000003371 meters per second squared. What that basically means is the number of decimal points here, you can just kind of take the number of zeros after the decimal there. So 4 decimal points there. We don't even have 4 decimal points here. That means this is pretty spot on. Sorry, our acceleration is 2 times 0.015, which equals 0.03 meters per second squared, which, and it doesn't usually match this well, matches our prediction pretty well. All right, because we predicted 0.03. Okay, so we have done our analysis. Because we've commented on how we've calculated our acceleration. We've made our graph, which kind of gets made automatically as you collect data, and we also wrote a conclusion, a brief conclusion, about how well our data matched our prediction, which was really, really well. The last thing we need to do is make our PDF, so that we can pick, let's make our PDF. We'll go click Untitled, Export, PDF. One thing we want to make sure is that we say which video, what we're actually looking at here. So where would be a good place to put a title that shows up, I guess, right here in the data set. Rename it. Here we go. Rename it. This is ErgoBot Video 1. Don't forget your title. ErgoBot Video 1. Rename it. Okay. So here we go. Our notes still don't work, but we're going to click Save PDF and be done with it. All right. Thank you.